Hi everyone, this is my Lab 3 report. A quick introduction and the purpose of the lab in part 1 is to find the unknown mass of a black hole, and in part 2 we utilize the mass of the black hole to create a trajectory for a spaceship to get close to the black hole but still be able to leave its orbit and not get sucked in. Some of the fundamental physics principles utilized are the momentum principle, where F net is equal to dp dt, and F net is equal to its perpendicular and parallel components, and the same goes for dp dt. We also utilize the velocity update formula, where we can find a final velocity if we have its initial velocity, the net force, mass, and change in time. And we also utilize the position update formula with a non-constant net force, where we can find the final position of an object if we have its initial position, its final velocity in this case, and change in time. Lastly, we also have the universal gravitational force, which is the force felt by the system due to the mass of another object, with the formula below. And we actually rearranged the formula in this case to find the mass of the black hole. A quick model description in part 1 is that we utilize the gravitational force formula, net force, and Newton's second law to solve for the unknown mass of the black hole. And in part 2, we utilize the same formulas to visualize the motion of the planet and spaceship, which allows us to find the required velocity of the spaceship to get as close as possible to the black hole without getting sucked in. A quick overview of the results in part 1 is that we needed to calculate F net parallel, and F net perpendicular to calculate the average mass of the black hole, since we get a mass calculation during each time step, and you can see the average mass of the black hole below. We needed to calculate F net on the planet and F net on the spaceship for each time step in order to use trial and error to figure out the velocity of the spaceship that would bring us as close as possible to the black hole without getting sucked in, and you can see the initial velocity below. A quick methodology is that we first look at the initial conditions in part 1 of the lab, where we have the gravitational constant, the mass of the star orbiting the black hole, and the delta T. And then we move into the calculation loop, where we compute the momentum, the change in momentum and velocity, then compute both F net and dp dt, and then we compute their parallel and perpendicular components. And after all of those calculations, we can then compute the mass of the black hole. So this is the output that we get from part 1, where we can note that the closer the star is to the black hole in its orbit, the higher the mass of the black hole is, and vice versa, which gives us the mass of the black hole in its average form. So moving into part 2, we see that some of the initial conditions are the mass of the black hole we calculated in part 1, the known constants that were given, the planet initial conditions, which include its speed and velocity, and then also the spaceship initial conditions, which are the speed in the x and y direction and its velocity. So moving into the calculation loop in part 2, we first calculate the net force on the planet, which comes from the force of the black hole on the planet and the force of the ship on the planet. And then we do the same for the spaceship, which comes from the force of the black hole on the spaceship and the force of the planet on the ship. And lastly, we also apply Newton's second law to update the velocity and position of the planet and the spaceship. So this is the output that we get from part 2, with the full view and a closer up view of the spaceship's trajectory. And the key note here is that the trajectory came from trial and error with the initial velocity, but the y speed always needed to be higher than that of x, and the velocity in the x direction had to be negative in my case. So some of the results in discussion is that some potential sources of error in parts 1 is that the average mass is not equivalent to the actual mass because it's an estimated value, and this kind of compounds into part 2, whereas using an estimated value could have changed some of the calculations for initial velocity, as well as the gravitational forces that the black hole has on the planet and spaceship. So in conclusion, we have the what does it mean question that relates the net force and the rate of change in momentum. And in the lab, we see that technically they are equivalent, but the main difference is that we're able to actually directly calculate dp dt, whereas we concluded that F net must be equivalent. Therefore, we see that dp dt was measured and net force was deduced from that measurement. And lastly, we have the what if question, which I used the below initial velocity to find some sort of orbit of the spaceship around the black hole where it still wasn't crashing. Thank you.